In Chapter 3, we're going to start to learn some shortcut formulas for calculating a derivative. Up until now, if we wanted to take a derivative, we had to set up and evaluate the limit of the slope of the secant line. There's some nice algebraic shortcuts for getting to that result, and we're going to start learning those in section 3.1. In particular, we'll learn them for polynomials and exponential functions. Now, some of you will say, oh, wonderful, we never have to take the limit of the slope of a secant line again. That is not true, okay? If, in the future, you're asked to take the derivative of a function, you may use any of the tools that we've learned this semester, okay? However, if you're asked to evaluate a derivative by using the limit definition or by evaluating an appropriate limit, I'm asking you to do it the way we did in Chapter 2, by taking the limit of the slope of the secant line. That's a really important skill because the shortcut formulas are very efficient. We can calculate things very quickly, but they sort of obscure what's going on. They don't show that we're actually measuring this geometric thing. Whereas when you're taking the limit of a secant line, you're always thinking about, I hope, that geometry of what the derivative means. All right, I'm going to actually start with a very simple function. It is a polynomial. It's a 0-degree polynomial. We're going to look at a constant function. Okay. So if f of x is equal to c, just a constant, I know that the graph of that is just a horizontal line at height c. So that actually has a slope, and the derivative was generalizing the slope, but generalizing it, that notion of slope, from a line to a curve. So it kind of makes sense that the derivative of a line ought to be the slope of that line. So it seems like we ought to be getting just 0 for the derivative. Because if I have this function and I choose a point, let's say this is my x value, okay, it looks like the tangent line to this curve would be the line itself, and that would have a slope of 0. But let's actually confirm this algebraically. So here's my point x, and then of course the y value is just c. Here's x plus h. And of course the y value is just c. So yes, the secant line is actually exactly that line. And so f prime of x would be the limit as h approaches 0 of rise over run. So that's going to be c minus c over x plus h minus x is just h. So that's the limit as h goes to 0 of 0 over h. Now that's kind of interesting because it doesn't look like that h is going to cancel the way we usually do. I don't have an h on top, but I suppose I could say that 0 is the same as 0 copies of h. I'm going to look at this one a little bit more graphically. If this were my h-axis, because I'm really viewing this as a function of h, this is clearly undefined if h is 0, because I cannot have 0 in the denominator. But for any other number h, 0 divided by that number is 0. So what the graph of this function, 0 over h, looks like is it's just the h-axis with a hole in it. And if I take the limit as we approach 0, I'm expecting there to be a point there. That's going to be 0. Okay. So notice if you get that the top is not just going to 0, but the top is exactly 0. But the bottom is just going to 0. Okay. This fraction will be 0 everywhere where it's defined. So if the top is 0 and the bottom is merely going to 0, the limit of that fraction is 0. Which confirms what we expected, that if you have a horizontal line of slope 0, the derivative is the same as the slope. And in the next video, we'll look at lines in general and see that the derivative of a line is in fact the slope of that line.